Okay, welcome class to Physics 390, Quantum Mechanics, class number 1. And it's a pleasure to be your instructor this semester, and I look forward to some very interesting discussion and of the concepts of quantum mechanics this semester. So this will be just an introduction to some aspects of the class, and then we'll look at the Schrodinger equation and its interpretation and some aspects of probability theory. So this recorded lecture covers chapters 1.1 to 1.4 in the textbook, and I'll refer to a couple of proofs from the textbook for that. So, okay, without further ado, here we go. So in an overview, this class is going to take the format of a flipped classroom. So you're going to be watching lecture videos beforehand and then working problems in groups during class, okay? So I won't be lecturing. I might say just a few words at the beginning of class, but generally I won't be lecturing during class. You'll take care of that out of class. And then in class, you'll be working problems in groups to get more experience in your hands really into the material. And there's a lot of evidence that this leads to a stronger grasp of the material because you get kind of 2 passes through it. You get to watch the video before class, come to lecture or come to class, and then work problems based on that material. And so anything that you didn't get in the lectures that you watched is bound to come up in the problems. And so you can ask for clarifications. So you kind of get 2 for each class watching the lecture video, and then doing the problems in class gives you 2 passes through the material. So it leads to a stronger grasp. So this class is going to be a more in-depth study of quantum mechanics than you saw in modern physics, Physics 203. We'll be looking at both conceptual foundations and also applications to a variety of systems, physical systems. And I should say that in the conceptual foundations, we'll look at the basic conceptual foundations, sort of the postulates of quantum mechanics. But at the end, we'll also briefly examine some of the modern issues that are still active areas of research. And there'll be a group project where you can explore some of those areas that or areas of the theory that we don't fully cover in your group project at the end of the semester. So hopefully that'll be an interesting way to conclude the semester. Mathematically, the mathematics will include differential equations, some linear algebra, and Fourier analysis, and of course some regular algebra too. But so your background from Physics 270, mathematical methods, will be very helpful since you covered those topics in Physics 270. So, all right, let's start off with the Schrodinger equation. If we have a particle of mass m represented by this little kind of car or truck here, and it's subject to a conservative force F, which is equal to minus the partial of a potential with respect to x. So remember, any conservative force can be written as minus the derivative of a potential with respect to position. And fortunately, this semester in quantum mechanics, we'll only really be dealing with conservative forces like the electrical force and the spring force. And on the microscopic level, where quantum mechanics is used, all the forces are conservative. Air resistance and friction come about at the macroscopic level. So we can pretty much assume conservative forces and potential energies, valid potential energies. So what would we do with this classically, this mass m subject to this conservative force? Well, we'd use Newton's second law, which is that the mass times F equals ma. So the F is the minus the partial of v with respect to x, and then m times a, where a is the second derivative of the position with respect to t. So m d squared x dt squared is minus dv dx. And along with some initial conditions for x and either x at 2 points or x, the initial velocity in the initial position, we would get x of t. So the position as a function of time. Once we had that, we know how to get the velocity from the position as a function of time, just taking the time derivative. We can get the momentum from the velocity just by multiplying by the mass. And we can get the kinetic energy by taking 1/2 the mass times the velocity squared. So we can get all these quantities directly from x of t. Quantum takes a different approach. It also involves solving a differential equation, but it's a little more indirect how we get to the physical quantities. So in quantum, as you may remember from modern physics, our goal in solving the Schrodinger equation, as opposed to Newton's law, is to find what's called the wave function, which contains all of the information we have about the state of the particle. And it involves, we find the wave function solving the Schrodinger equation, which is this equation here, I h bar d psi, where psi is the wave function dt, is equal to minus h bar squared over 2m second derivative of psi with respect to x plus the potential energy, which we're talking about up here, times psi. And just keep in mind that h bar is Planck's constant h over 2 pi, which is a very small number, which is part of the reason we don't see quantum phenomena on an everyday scale. But anyway, this wave function is a little different than the position function. The position function is something that's kind of real and in space, right? We can visualize that. But the wave function is kind of an abstract concept. And we extract information about the position, velocity, momentum, and the kinetic energy from the wave function using special rules that we learned a little bit of. You learned a little bit of in modern physics, but we'll review and get in more depth in this class. Okay, so that's just contrasting how we deal with a particle in a conservative force classically and quantum mechanically. Quantum mechanically, it's a little more abstract. We get this wave function first, which is a little bit, takes some getting used to, and then we learn rules for extracting the position about the physical quantities from that wave function. Okay, so as I said, this wave function is a bit abstract. What does it represent? So what does this wave function tell us? Well, and you may remember this from modern physics, but I want to review it here. It really tells us directly the probability of finding the particle at different positions in space. Okay, so for example, here is it's actually the wave function squared, and technically the wave function is a complex function, and we'll get into that later. So this wave function squared is actually the modulus of the complex function squared, but don't worry about that too much now. We can just think of it as the wave function squared. So this is a graph of the wave function squared versus position. And where the wave function squared is big, like at point A, it's very likely to find the particle. Where it's small, like at point B or even point C, it's not so likely to find the particle. And so we can say that we can make that mathematical by saying that the probability of finding the particle between 2 points A and B, little a and little b here, the shaded region here, is the integral from A to B of the square of the wave function. Okay, and we'll see in a minute that that corresponds to something called a probability density, a probability per unit interval of length. So anyway, conceptually, the wave function tells us the probability of finding the particle at different positions in space, where that probability can vary from position to position. All right, so this poses some interesting questions. There's since the particle can be measured at different points in space, there's an indeterminacy in the result of a measurement. Okay, so that is, if we take the same system or 10 identically prepared systems, we measure each of them, we get a different result for the position in each. So there's indeterminacy in the result of a measurement. And that certainly was a big area of debate as quantum mechanics was developed initially, and to some extent remains an area of debate today. But some of the different schools of thought initially were where there were three, at least three that are described in our textbook. One is the realist position. And that position says that even before the measurement we make, the particle is at a definite position. And then when we measure it, it just materializes at that position. So this is saying now that position can vary but it's determined, it exists before our measurement. So our measurement doesn't do anything to the system except reveal a property which is already part of the system. So in this case, quantum mechanics would work because it gives distributions which agree with experiment, but it's incomplete because there must be some property of the system, which determines this definite position before the measurement. And the wave function doesn't include that. So the wave function would be an effective but an incomplete description of the physical system because it doesn't contain that definite position. All right, moving on. The orthodox interpretation or different school of thought said that no definite position existed before the measurement, and the act of measurement would force the particle to choose its position. Okay, so this is contrary to the realist position. The particle exists sort of in a ghostly, fuzzy, indeterminate state before the measurement, and it's the actual act of measuring it that forces the particle to choose according to the distribution that the wave function squared indicates. And this is the popular so-called Copenhagen interpretation, because it originated with Niels Bohr and his colleagues in Copenhagen in the, early decades of the 20th century. And last was sort of a third school of thought, which is kind of agnostic, which is say it's not really meaningful to ask what existed before a measurement, because the only way we can, in science, we can test things is to measure them. So what exists before the measurement can never be tested. So it's not really meaningful to ask whether there's a definite position before the measurement or not. So that was a third school of thought. So kind of interesting philosophically to think about these things. So something really amazing happened. In 1964, a physicist named Bell came up with a theorem, which we'll look at later this semester, at least the beginnings of it. And it had to do with some probabilities of different possible measurements in carefully prepared systems. So Bell's theorem has to do with different probabilities and how those probabilities add up and compare to each other. And Bell's theorem and further experiments which tested it actually implied or supported only the orthodox view that no definite position existed before the measurement. It was able to largely rule out the realist position that a definite position existed before the measurement in a very, very clever and interesting way. So the orthodox view, the Copenhagen interpretation, is the view that most physicists hold today. Although alternatives do exist, there are just two of them are Bohmian mechanics and the many worlds interpretation. So someone might explore, some group might explore some of those alternatives in the group project at the end of the semester. So, okay, that's a little bit about the philosophy of quantum mechanics. We'll talk more about that later at the end of the semester and perhaps in your group projects. Okay, so some really interesting experimental confirmation and a beautiful experiment is two-slit electron diffraction, which was finally experimentally realized around 1970 when the necessary technology was developed. So this is a picture of um, a plate which is exposed by electrons impinging on it, and the little dots of little dots you see are electrons actually at hitting different locations of the plate. So gradually, the electron builds up an interference pattern. Here's 8 electrons, 270 electrons, 2,000, then 160,000. And gradually becomes more and more apparent that there is a variation in space of the intensity of the electron density, okay? So these electrons are actually showing wave-like properties, because light, when it diffracts through slits, shows this kind of alternating pattern of, in that case, dark and light. In this case, it's the density of electrons hitting this photographic plate. So just a couple of details of the experiment. You can reduce the intensity of the electron beam until on average, less than 1 electron is passing through the 2 slits at a time. Okay, so it's not like there's lots of electrons going through and they're interfering with each other. On average, less than 1 electron is passing through the 2 slits at a time. So each electron is actually interfering with itself. It's passing through both slits as a wave, and then when it hits the screen, or when it reaches the screen, that wave that it's being guided by, or its position is being determined by, collapses to one of these points. And the pattern eventually seen, the one seen in part D here, is the one predicted by the Schrodinger equation, which is a wave equation, and the statistical interpretation of the wave function, which we just talked about, which is that the square of the wave function is the probability density of seeing that particular, seeing the electron in that particular place. And as I mentioned, each individual electron has its position determined by the wave function, but it's detected as a discrete blip or dot here on the screen. And that's generally true when particles don't interact with matter, like a screen. They evolve according to a wave equation, because particles, as you remember from modern physics, are both waves, or entities like the electron are both waves and particles. So when they're not interacting with matter, they evolve like waves. And once they interact with matter, like a solid surface, they interact as a particle. So they show up as a discrete blip. Okay, so this is a real confirmation of some of the ideas, the Schrodinger equation, the statistical interpretation, and this amazing fact that individual electrons actually, single electron can interfere with itself. All right, so let's go over a little bit of some mathematics that is useful in describing the wave function and the information we get from it. So we're going to start off with discrete variables and some probability. So let's say we have a group of young people, like, you're a quantum mechanics class, for example. You guys are all young people. And of course, there's some younger people here. We don't have any 14-year-olds, but we do have some, well, I don't know. Actually, there's a gap in the college age. But anyway, these are roughly your ages. So this is the distribution of ages in a group of young people. We have a 14-year-old, a 15-year-old, three 16-year-olds, two 22-year-olds, two 24-year-olds, and five 25-year-olds. And you can see a histogram up here in the top right hand corner of the different ages. So 1 for 14, 1 for 15, 3 for 16, and so forth. Okay, so the total number of young people in this group we would get by just adding up all these numbers. 1 plus 1 plus 3 is 5, plus 2 is 7, plus 2 is 9, plus 5 is 14. So we have 14 total young people, just adding up this column of numbers. And in general, we can express that by saying that the total number would be the sum over all the ages, j equals 0 to infinity, of the number of people, of young or people with that age, So we just sum up over all the ages, the number of people with that age. So this would be the notation we would use. N equals the sum from j equals 0 to infinity of n of j. Another interesting quantity is the probability of a given age. The probability of a certain age would be the number of people at that age, n of j, over the total number of people. So just as an example to illustrate that, the probability of a 16-year-old in this group of 14 young people would be n of 16, which we see as 3, over n, which we see as 14, so 3/14. So 3/14 would be the probability of, we selected one of these young people at random, that they would be a 16-year-old. Okay. And the average age is important because we often look at average quantities in quantum mechanics. So how would that work? Well, so if we look at here age 14, there's one person age 14, so we just add in 14. Age 15, there's one person, so we just add in 15. But there's 3 people with age 16, so we'd want to add 3, sum up 16 3 times, because there's 3 individuals here. There's 2 22-year-olds, so we multiply 22 by 2. We multiply 24 by 2. We multiply 25 by 5. So we're going to multiply each age by the number of people with that age to get the total collective age of the group, which happens to be 294, if you verify that. And then we're going to divide that by the total number of people, which is going to be 14. So 294 over 14 is 21. So the average age of this group is 21. So how would that work in a formula? Well, we would represent the average age with these brackets, and these will become very familiar as the indication of an average. So it'd be the sum of each particular age, j, so 14, 15, 16, etc. But in general, all the ages, times the number of individuals with that age, to weight that age by the number of times it occurs, to get the total collective age, and then divide by the total number of individuals to get the average age. And then notice, since the quantity n of j over n is p of j, the probability of a given age, we can replace n of j over n by p of j. So this is sort of a more compact result, which says that the average age j, or bracket j, would be the sum over all possible ages of each age times the probability of that age. So it's a weighted sum of each possibility times the probability of that possibility. This is a very general result. We'll see it come up in quantum mechanics. It also comes up in thermal physics, in case some of you have had that class before. I know some of you will be taking it later, but anyhow, that's very useful. Okay, so we can generalize this actually. It doesn't have to just be the age itself. It could be any function of the age that we take an average value of. So for example, we could take the average of the age squared. f of j would be j squared. And then if that were the case, then this would be the sum from j equals 0 to infinity of j squared p of j. So any function of j can just be plugged into this point here and will give a valid answer. Okay, and we can use that fact to get a handle on not only the average age, but the spread of ages. Because here's 21, but they're spread out pretty far around 21 here, as opposed to being clustered really close to 21, like our class, our quantum mechanics class would be. Okay, so what we can do is look at what's called the deviation. Delta J would be, for a given individual, would be that individual's age minus the average age. So for 25, a 25-year-old, that would be 25 minus 21, or 4. For a 14-year-old, it would be 14 minus 21, or minus 7. Okay. And then because we don't really care for the spread, whether the age is greater or less than the average, we do a little trick, and we take the average of the square of this deviation. So you see this, here's this deviation delta J, we square it. Okay, we square it. That means it doesn't matter if it's plus 4 or minus 7, it's still going to contribute positively to the spread because we square it, and a positive or a negative number squared is positive. So we take the average of it squared, which is called, which we represent by sigma squared, and that's called the variance. So sigma squared is the variance, and its square root, sigma, is our usual measure of the spread, because sigma squared would have units of age, in this case, age squared, if we were looking at distance squared. And we want our spread to be age, or in the case of position, distance. So we take the square root of sigma squared to get the usual measure of the spread. And the term for that is the standard deviation. And then the standard deviation, sigma here, we can certainly calculate it by using this formula, the square root of delta J squared, where delta J is this formula here. But there's, it's shown in the book that if we take this formula here with delta J plugged in here squared and do some simplifications, we actually get a nice expression for the standard deviation. It's the square root of the average value of the square of the quantity minus the square of the average value of the quantity. Okay, so the average value of in this case age squared minus the square of the average value of the age, and all that, the square root, would be our spread. Okay, all right, so that's some discrete values in probability. Let's look at continuous variables and something called probability density, because position is not like age. Age is 1, 2, 3, 4, 5, 6. It's a discrete quantity, whereas position can take any value in a continuum. So in that case, so this is a graph or a plot of the relative probability of the measured heights x fallen for a dropped object. So the object is dropped from x equals 0. So that would be the initial drop height, and it drops a height h. Okay, and so this is the relative probability if we just pick a time at random during the fall and we measure the height, what the probability of measuring different heights x would be. And since it spends more time near the top height, or near its initial position at x equals 0, because it's moving more slowly there, because as you know, it accelerates as it gets further down toward the ground, we're going to get a higher probability of of observing it at the near x equals 0 than we get at x equals h. So this probability, relative probability, we'll call it right now, decreases as we get closer to the ground because it's moving faster as it gets closer to the ground. And so it's less likely in a random sample that we'll see that. Okay, so in fact, this is a probability density because the probability of finding any one particular height to the nth infinite decimal place is actually 0. We're always dealing with a range. And so the probability density reflects that. It says that the probability density rho of x is defined by the probability that an individual measurement of the height chosen at random lies between, say, x and x plus dx, a small interval here, is the probability density rho x times dx. So what does that mean the units of probability density are? Well, they would be probability, which doesn't have any units, divided by dx. So in this case, divided by length. So the probability density would have units of 1 over length, or probably most likely 1 over meters. So it's the probability per unit, unit interval on the of the measured variable. So that's why it's called the probability density, because it's the probability per unit of the measured variable, not a strict probability, but a probability per unit of the measured variable. Okay, so some properties of the probability density. So the probability, the total probability between, say, 2 points A and B, so let's say this is point A and this is point B, would be the integral of the probability density between those 2 points, okay? So we just integrate the probability density with respect to the measured variable to get the total probability between two values of that measured variable. And there are similar analogous relationships to the discrete case, which we just discussed, for the total probability, for the averages, and for the variance, and then the standard deviation, which comes to the variance. So because the total probability has to be 1, that is, the variable has to be measured with some value. If we integrate over all possible values of the variable of the probability density, we must get 1, okay? And this is often called the normalization of the probability density, because it's so normal when the integral is equal to 1. The average value of x, we would take as the weighted average of each x times the probability of getting that x, which would be the probability density times the little dx that we're looking at. So this rho of x dx is the probability times the value of x, add those all up, integration, and that's going to give us the average value of x. And then, as before, we talked about, it doesn't have to just be x that we take the average value of. It could be any function of x, like x squared or x to the 5th, or I don't know. You can make up your own function, sine of x, whatever, is the integral from minus infinity to infinity of, instead of x rho of x dx, it would be f of x rho of x dx. So again, we're taking rho dx as the probability in that small interval dx, multiplying it by the value of the function, and then adding up all of that to get the average value of the function given the distribution, the probability density rho of x. So using that, we can define the variance, and from the variance we can get the standard deviation just by taking the square root as the average value of the deviation, which would be x minus the average value of x, just like in the discrete case. And just like in the discrete case, you can show that the average value of delta x squared, the deviation squared, is actually the average value of the square of x minus the square of the average value of x. And that's this last one is the easiest one to calculate. Okay, so that's continuous variables and probability density, as opposed to discrete variables and probability. Okay, so let's just wrap up by applying this to the normalization of the wave function, kind of tying back to what we were doing before. Now that we've just done some mathematics of discrete and continuous probability and probability distributions. Remember, so we can say that psi, the wave function squared, is the probability density for finding the particle at position x at time t. Okay, because it's we saw before that the postulate was that psi squared dx was the probability, but that's what we mean by the probability density. So the square of the wave function is the probability density for finding the particle at position x at time t. And so we must have, because this is just an example of the normalization we were just talking about, the integral from minus infinity to infinity of rho of x dx is equal to 1, where rho of x here is psi of xt squared, the square of the wave function. And this is the normalization condition. Now, why is this important? Well, the Schrodinger equation is linear in psi. Psi only appears, there's no psi squared or psi cubed, it just appears as psi. And that means that if psi is a solution, then any constant a times psi is also a solution. So in other words, we can scale down the solution by using an a that's really small, or make the solution really big by using an a that's really big, and it would still solve the Schrodinger equation. But that would, if we multiplied the wave function, excuse me, by say 2, the wave function squared would get multiplied by 4, and so we'd have the integral here, if it was 1, would become 4. And so we'd have the total probability being 4, which just doesn't make sense. Probability should be 1. So there's a unit chance of finding any particular or any value. So this process of normalization is determining this constant a, so that the probability density integrates to 1. Okay, so that when we find a solution to the Schrodinger equation, often we have a constant a, which is out in front and undetermined, and then we use this normalization condition to that the integral here should be 1 to determine what a must be. And we'll see examples of this in future classes. If you remember, if you happen to have a good memory and you go back to modern physics, we looked at it in the case of the one-dimensional infinite square well, where the value of a turned out to be the square root of 2 over the length of the square well. But we'll be going over that again. So if that rings a bell, that's great. If not, we'll be looking at that again. And then last point, it's proved in the textbook that if normalized at an initial time, the Schrodinger equation guarantees that the wavelength will remain normalized at all future times. And that's important because if we have at time 0, say this held, and then the Schrodinger equation as the wave function evolved changed the value of this integral, then the probability, the total probability, which started at 1, could vary from 1, which wouldn't make mathematical or logical sense. But it's possible, I'm not going to show it here, but it's shown in the textbook that if you take the time derivative of this integral here and use the Schrodinger equation, you can show that the time derivative is 0. So that means that if it starts out at 1, it remains at 1, and we have a a consistent normalization if we start out normalized. Okay, so in summary, we've looked at the Schrodinger equation. We've looked at how to approach a conservative force with classical and quantum mechanics. We've looked at some interpretations or schools of thought on what the wave function and measurement meant. We talked briefly about Bell's theorem and experiments which shed light on this, and we'll talk more about that near the end of the semester. We looked at discrete and continuous distributions and talked about what probability density is and connected that to the square of the wave function, which is a probability density, and the process of normalization. Okay, so hopefully that's a good kind of review and somewhat refresh your memory and maybe a few new things to whet your appetite for the semester. Next time we'll be determining the momentum. We'll learn how to determine the momentum from the wave function psi, and we'll also take our first look at the uncertainty principle. Okay, thank you guys for listening, and I look forward to seeing you in class.